Cool. All right, so we're gonna keep working through lecture set 2 today. I just wanted to remind you guys of a few details. So the first assignment is due on January 22nd, which would be next Friday. So the first assignment is essentially going to cover the materials in lecture set 1 and let's say like the first 2/3 of lecture set 2. It's basically, some preliminary definitions and some of those fundamental concepts being applied to a real life example. And then it's questions regarding the properties of simple random sample estimates or estimators. And then it's some questions asking you to apply simple random sample estimators to a specific data set that I provided to you on the course website. So that's again due next Friday at the end of the day. And that's to be submitted through Crowdmark. And again, right now we're just working through lecture set 2, which is the simple random sampling unit, and that would correspond to chapter 2 of the lower textbook. I want to try this semester to give kind of like end of the week updates at the start of class, and then I'll post a little blurb afterward just to try and help students stay on track. I would imagine at this level it's not as big a deal because I would expect that most of you are probably pretty organized as it is, but just something that I wanted to try this semester with the online style. Okay, so all of that being said, again, it sounds like most of you guys can hear me, and I assume that you can see the slides based off of some of the earlier comments, so I'll just get going. So last class, we had defined what we had done last class is we finished up lecture set 1 and we moved into lecture set 2. At the start of lecture set 2, we effectively described what probability sampling is in a very general case. So we said, imagine that you have a population or a sampling frame with capital N units, and then consider all of the different samples that could be collected from that frame. So for example, on the slide here, if we have capital N equals 3 different units that are available to us, and we call these units, say 1, 2, 3, or Y1, Y2, Y3, then there are 7 different possible samples that we could observe. We have 3 samples with 1 element, we have 3 samples with 2 elements, and then we have 1 sample with 3 elements. And then we defined some estimators. Now, as a reminder, we distinguish between the parameter, the estimate, and the estimator. So we have capital mu, we have mu, which in pretty much every statistics course designates the population mean. So as an example, if we wanted to consider the population mean, we would use mu to designate the parameter of interest. And again, the parameter is an unobserved random it's an unobserved quantity that we are interested in making a statement about. The truth is, sort of just on a side note, most often we assume that mu is a fixed quantity, so it's a value that does not change, but there is another paradigm of statistics called the Bayesian paradigm, where you would assume that mu or the population parameter is actually random as well, and you have different inferential techniques that fall out of that philosophy. Anyway, in our study, we assume it's a fixed quantity, and then we construct an estimator that will allow us to calculate a value of that fixed quantity based off of a sample. So the idea here is essentially that the estimator is, like the tool or the formula that we utilize to collect our information. And the estimator will produce the estimate. So the estimate is, again, a fixed quantity, but it is the quantity that is corresponding to the sample that we have actually collected. So the estimator itself is a random variable because its value will change with each of the different samples that you collect from. Whereas the estimate is a fixed value because it is a function of the sample that you have selected. Now, in terms of notation, we use 2 very slightly different symbols to differentiate between the estimator and the estimate. So the parameter will just be the symbol itself. The estimator has a tilde that sits on top. So you can see on the slide, on slide 11, right here, we have this little tilde symbol that represents the estimator, which again is basically just the function or the tool that we are using to compute the estimate. And then the estimate itself has a hat that sits on top of the symbol, and the hat represents estimate of. So that would be an actual fixed quantity. All right. So given our definitions of sort of the general probability sampling scheme, we then established that each different sample from the frame is going to have some probability of being selected. And then from that, we can work out the inclusion probability, which is just the probability of a unit being selected. So the inclusion probability is the probability of an individual unit from the frame being selected for the problem. And the sampling probability, or the probability of observing the sample, is, well, as I just said, the probability associated with each of the different samples that could arise from the frame. Now, these again are very simplistic ideas. We have very small frames. What we're going to progress towards are situations where the frames are much larger, and we can't necessarily write out the probabilities in the way that we can here, but we can assume probabilities and then collect based off of those assumed probabilities. Okay, on slide 11, we have an illustration of how our estimator formulas would apply to one of the samples that we have collected. So you can see here, if we consider sample 1, 2, these two illustrations show that we have selected an estimator. So for mu, we have selected 1 over n times the sum across each of the observations in the sample. This would just be the general definition of the sample mean. And then we show that the estimate based off this estimator, if we let y1 and y2 be 1 and 2 for illustrative purposes, is 3 over 2. This could also just be the average of y1 and y2 if you want to assume that they are unitless values, for example. And then similarly, if we wanted to estimate the variance, we select the estimator 1 over n minus 1 multiplied by the sum across the samples of yi minus mu all squared. This is just the defining formula for the sample variance. And then our estimate becomes similar to the estimate for mu. In this case, it basically just becomes the sum of the squared difference of each observation around the mean, which works out to be 1 over 2 in the context of the example if we let y1 be 1 and y2 be 2. All right. So we can apply a similar idea if we wanted to see illustrations of other sample estimates based off of the different samples in this particular illustration. All right, now when we select our estimators, we actually have different types of estimators that can be used for the same population quantity. Now, with the mean, this isn't something that we come across as often because usually we focus on the average value of the sample, which is just, again, the sum across all values divided by the sample size. That's a very common estimator for the sample mean. And we can show that it has very good properties. For the variance, you can actually show that the estimator that we utilize, where you have 1 over n minus 1, is a corrected estimator, because the actual estimate for the variance based off of the definition of variance is biased for the population variance. So that is the traditional estimator of variance that you see in Stat 151 and Stat 252, and the estimator that we used on the previous slide. This actually corrects the true estimator for being biased. So this is this isn't the actual derived estimate of the variance, it's a corrected estimate, because the derived estimator is actually unbiased. It is actually biased, sorry. All right, so what does that mean? Bias, unbiased, what are the other properties of a good estimator? So in general, we consider there to be we'll consider three different ways of describing an estimator. We can describe it in terms of its bias or lack thereof, its precision, or its accuracy. So the illustration on slide 12 shows 3 different dartboards. And on the dartboards, you can see that there's a number of different X's, which would represent where the estimates line up relative to the population parameter of interest. So let's consider on these illustrations the bullseye of the dartboard to be the population parameter of interest. So this could be mu, or it could be sigma, or it could be sigma squared, for example. We'll define, just for in general terms, the value theta to just be some parameter of interest. So let's make a note over here. So we'll say let theta be population parameter of interest. Okay, so then if you want to, at the center of the dartboard, you can just sketch a theta. Okay, so the bullseye represents the population parameter, so the target, if you will. All right, now, what do each of these dartboards represent in terms of those 3 different definitions that or those 3 different describing terms that are given above? Well, Archer A, you can see if you were to average across each of the marks on the dartboard. So consider, let each X be a estimate. Okay, so if you were to average across each of the different X values on Archer A, this would be an example of an unbiased estimator. So the estimator that was used to compute the value that ends up being one of the X's on the dartboard, that estimator would be unbiased for Archer A, because if we were to take the average of each of those different X marks or each of those different estimates, they should average out to right around the bullseye. Okay, so the idea of being unbiased means that if you were to compute the average of the estimate across all possible estimates, you would end up at the true value. Now for Archer B, in contrast, this would be an example of a biased estimate. This estimate is biased because if you were to take the average across all of the different marks, the X marks on the dartboard for Archer B, this would clearly not average out to be equal to theta, right? This is going to average out to be somewhere here, for example. So this would be the location of average value of estimates. Okay. And then in contrast here, this would be location of average value of estimates. All right. And then for Archer C, this again, like Archer A, would be unbiased. For the same reason as with Archer A, you can see that if you were to average across all of the different marks on the sample, this value would be roughly at the bullseye, or actually in this case would be probably exactly at the bullseye, which would be the true value. So the idea of being unbiased means that the average of all possible estimates would be equal to the population parameter. And we'll define this more strictly in terms of our expected value notation momentarily, though I assume that most of you have probably seen this definition before. All right, so we've established that Archer B is the biased collection of estimates, or the biased estimator, and Archer C and Archer A are unbiased. Now we can go a little bit further and we can continue to describe what we are observing in terms of the terms precision and accuracy. Now, to be fair, the precision the term precision and the term accuracy are terms that I often confuse when I'm teaching them without this illustration. So to try and help us understand these, we can start by noting that precision refers to how close together the values are. Accuracy refers to how close the values are to the, how close together the values are, given that they are close to the center, or given that they are close to the parameter of interest. So for example, in Archer A, this would be an example of a situation where we have an unbiased estimator, not animator, that is not precise. Okay, so the average of these estimates, again, should be right around the center or right around the true value, which is what you would hope for. But we are lacking precision because you can see that the estimates are spread out, or you can see that the estimates are quite spread out across the dartboard. Whereas if we compare to Archer B and Archer C, these are both illustrations where we have precision. So the idea of being precise means that the collection of estimates are close together. So they're in the same area as one another. So Archer B shows a biased illustration so again, the estimates are not close to the true value, but they are precise because they are close to one another. So this would also be an illustration where the estimator is not accurate. So accuracy refers to all of the values being essentially precise and close to the population parameter. So in the last case, we have an unbiased, precise, accurate estimator. Okay. So does anyone have any questions about those ideas? No, it's not precise, so it can't be accurate. That's why I think I often confuse them as well. No, in this case, precision refers to the estimates, each of the different estimates from the estimator of choice being close to one another. So we're really talking about the features of the estimator, which is a function which will give a different value for each of the different possible samples within the population. So again, the precision refers to the estimator returning values that are very similar to one another across all possible samples. No worries. Any other questions? All right. Okay, so from a theoretical standpoint, what we're going to be interested in is defining, is giving mathematical definition of what it means to actually be unbiased, and how and use another mathematical definition to determine whether or not the estimate is more precise than another one. Now, this is where it gets a little bit confusing. Again, going back to Joel's question about the sort of differentiation between precise and accurate. Now, effectively, in practice, what we do is we first determine if the estimator that we are using is unbiased. So if the estimator is unbiased, that means that we have proof that across all samples, that estimator is going to return values that average out to the true value. When it comes to determining if the one estimator is more precise than the other, this effectively means that given we have an unbiased estimator, we need to determine which estimator has the smallest possible variance. Okay, so the two quantities that we are going to be most interested in computing are the expected value and the variance. Because again, if we can find an unbiased estimator, then the last part, or then all we have to do is determine which unbiased estimator has the smallest possible variance. And then we can say that this is going to be the best possible estimator for the parameter that we are interested in. And the rationale for that, once again, is that if the variance is as small as possible and the estimator is unbiased, then we know that that will be the most precise estimator based off of the illustrations that we had seen before and the definition of being precise. Okay, so again, accuracy comes into play with both the idea of being unbiased and the idea of being precise. So the accurate estimator is essentially is almost an umbrella term that includes unbiasedness and precision within it. If it's accurate, it has to be both of those things. But you can still have a precise estimate that's biased, so that wouldn't be accurate because it's not close to the center. All right, so how can we determine if the estimator is unbiased? That will require us to utilize our expected value formula. So the expected value of a discrete random variable, as you can see on slide 3, is the sum across all possible values of that variable multiplied by the probability of observing that variable. This is also called the average, or the average value for that variable. So what we will be interested in doing in the context of determining if a variable is unbiased is determining if the expected value of the estimator converges to the true value. Then we have the definition of the variance of the random variable, which you can see at the top of slide 13 as well. And what we will be interested in doing is for a collection of different estimators, determining which one has the smallest variance. Or in a practical setting, for a number of different samples, determining which estimator for the same quantity based off of those samples has the smallest variance. But that's something that we'll talk about a bit later in the course when we look at sampling using unequal probabilities. Well, when we look more closely at the idea of sampling using unequal probabilities for each sample. All right, so formally, if we have a parameter of interest, in the general case, say theta, and then we have some estimator, say theta tilde, we would say that theta tilde is unbiased if its expected value is equal to the true value, or to theta in this case. All right, so let's look at an example of how this would work. So going back to our previous illustration where we had a sampling frame with 3 units, and then we had all of our possible samples written out and the probability attached to each sample. We want to show that mu tilde is an unbiased estimator. All right, now this first part here is going to be a little bit confusing because I'm going to be using the same symbol interchangeably. Or I could use the same symbol interchangeably. So to try and just work past that so it isn't like why is mu tilde here and then again it's here with a different definition, let's just consider the following description. So the mu tilde as it's written on the slide here. Okay, so we'll star this value And we'll write let mu tilde s be the estimator of mu for each sample. Okay. And actually, let me just be very, very specific here. So you can see that the definition as it's written on the slide, this would be the definition for each individual sample. Okay. So this is the estimator of mu for each sample. We want to show that this estimator is unbiased. Now, from our previous discussion, we know to be unbiased, the average value of mu tilde across all possible samples must equal mu. Okay? So that's simply the definition of being unbiased. Okay. So the value as it's written on slide 14 here, the mu tilde, that is actually the estimator that we are going to use in practice, because that's the estimator for each of the different samples. To show that mu tilde is actually unbiased, we need to consider the average value of mu tilde across all of the different possible samples that it can be applied to for a particular frame or target population of interest. Okay, so given that definition, we can then say, therefore, mu tilde is a discrete random variable with I'll write it down here, with expected value equal to the sum of every sample in the frame of mu tilde s multiplied by the probability little s is equal to s. Okay. So effectively, all we're saying here is that to actually compute the expected value of the estimator, we need to consider each of the different possible values of the estimator across all of the samples multiplied by the probability of observing each of those samples. So in this particular case, we can see that the probabilities associated with the first three samples are all 0. Okay. So, sorry, I'm just going to move this over. Okay, so for example, in the first case, you would have, well, in the first case, the average value from the sample would also be, well, it would be y1 over 1, right? So let's write this as y1 multiplied by 0 plus y2 multiplied by 0 plus y3 multiplied by 0 plus, and then we would have y1 plus y2 over 2 multiplied by 1 over 4 plus y1 plus y3 over 2 multiplied by 1 over 4 plus y2 plus y3 over 2 multiplied by 1 over 4 plus y1 plus y2 plus y3 over 3 multiplied by 1 over 4. Okay. All right, now if we simplify this, we should be able to show that this thing simplifies to 1 over 3. Well, actually, let's write it like in y1 plus y2 plus y3 over 3, which is equal to mu. Okay, so I'll just give it a second in case anyone's copying it down, and then I'll just talk through it again. Okay, so again, what's happening on this slide is we are showing an application of the expected value operator. And what we are showing is, in a very simple situation, how we can determine if our estimator is unbiased for, in this case, the population mean. For the estimator to be unbiased, it means that across all possible samples from the frame, its value must converge to the population value of interest. So given the sampling, given the probabilities of each of the different possible samples from the frame of interest, we can show that the estimators that the estimate of the population mean multiplied by the probability of observing that sample summed together is equal to y1 plus y2 plus y3 over 3. And that is essentially every unit in the frame divided by the sample frame size, which is the definition of the population mean. So therefore, y1 plus y2 plus y3 over 3 is equal to mu, because that is the definition of the average across all possible values. Now, if you consider what's written down before we get to the final two lines here, we have y1 times 0, for example. This is simply value multiplied by probability of S. Okay, and then I'm just continuing that trend for each of the different samples. Now, if you want, you can, instead of writing y1 or y2, you can just write 1, 2, and 3. The only reason that I think it's better to write y1 and y2 here is because if you add too early, you're going to end up with an actual quantity inside of the brackets. And then when you go to simplify the expression, you're just going to end up with a fraction at the end. Whereas if you keep them as y1 and y2, you can see that the end result is y1 plus y2 plus y3 over 3, which again is clearly the definition of the population mean. So that allows us to say that we have an unbiased estimator in this particular case. All right. Any questions about that? Okay. All right, so the definition of a bias estimator is given on the first line of slide 15. So we have the bias of estimator tilde, or sorry, the bias of an estimator for some population parameter theta is equal to the expected value of that estimator minus theta. So you can see from the definition given here, if the expected value of theta tilde is equal to theta, right, which is the definition of being unbiased, then the bias of theta tilde is equal to 0. Okay. So in general, if we wanted to compute the bias for an estimator, we would have to first find its expected value, and then we would subtract the variable of interest. If that's equal to 0, then obviously we have an unbiased estimator, which is clear from the definition. And then if we do not have 0, then we have a bias estimator, and now we have a quantity that represents the degree of that bias. Okay, so to quantify the precision and the accuracy of the estimate, we can use two values, the variance and the mean squared error. Most often we'll just focus on one of these values and we'll compare them to one another across different estimators, but we can use each of them respectively to quantify the precision and the accuracy of our particular estimator. Okay, now again, we've already established that when something is accurate, it has to be, well, precise and unbiased. But formally, if we wanted to write down some definitions for this, we can show, first off, the variance will be computed in a very in a very familiar way. So the variance of an estimator is going to be equal to the expected value of that estimator minus its expected value squared. And this is basically just the general definition of variance, random variable minus its mean squared, and then the expected value of that quantity. So the variance, again, from a mathematical definition, is the average of the squared differences. And going back to the previous point that I was trying to make, when you actually work this out and you take the average of the squared differences, you'll actually find that the variance is biased for the population mean. So then it's corrected, and that's why you end up with the 1 over n minus 1. Okay, so the definition of variance is as written above. If you wanted to simplify this, you could, and you could expand the bracket notation out. So, just for the sake of completeness, we can also show that this would be theta tilde squared minus 2 times theta tilde times the expected value of theta tilde plus the expected value of theta tilde all squared, right? And then this is going to be equal to the expected value of theta tilde squared minus 2 times the expected value of theta tilde times the expected value of theta tilde plus the expected value of theta tilde squared, which becomes the expected value of theta tilde squared minus the expected value of theta tilde all squared. And that might be another formula that you're familiar with, sort of like the random variable notation of the computing formula for the variance. Okay. All right, so the mean squared error of an estimate is defined as follows. So we have the expected value of theta tilde minus theta all squared. Okay. So you can see that this is actually very similar to the variance, except that we're not taking the square difference around the expected value of the estimator. We're taking the square difference around the true value that we are interested in estimating. Okay, so if we start to break this up, we have theta tilde squared minus 2 times theta tilde times theta plus theta squared. Oh, actually, no, this is not going to be of assistance to us. Sorry. Okay, so to simplify this expression, apologies. So to simplify this expression, we're going to add and subtract 0 in the form of the expected value of theta tilde. There we go. Plus. There we go. Okay, yeah. So we're going to add or subtract 0 in the form of negative of expected value of theta tilde plus the expected value of theta tilde. Okay, now with this, we can show that this is equivalent to, oh, sorry. Okay, so we can show that this is equivalent to the expected value of theta tilde minus the expected value of theta tilde squared plus the expected value of theta tilde minus theta squared plus 2 times the expected value of theta tilde minus the expected value of theta tilde multiplied by the expected value of theta tilde minus theta tilde. There we go. Okay, and now the reason why we would want to write it in this form is because we can show that this quantity here, so the first part, this is the variance of theta tilde, and the second part is the bias of theta tilde squared. And then the last part, we should be able to show this goes to 0. So this would be expected value of theta tilde times this minus 2 times this. Yeah. So we should be able to show that the last part here goes to 0. So the mean squared error of theta tilde is equal to the variance of theta tilde plus the bias squared. So again, if we're using mean squared error to represent the accuracy, the accurate estimator is going to be one where the bias is equal to 0, and then the MSE converges to the variance. Hence the initial idea of the accurate estimator being one that is unbiased with small variance. So in the unbiased case, the MSE is simply the variance again. So it's an incorporated term, sort of an umbrella term for that particular quantity. All right, starting to get some heavier mathematics here. Nothing like that on a Friday morning, right? So does anyone have any questions about these derivations? Hopefully no one feels too much like this. Okay, so as we have established above, for the unbiased estimator, the mean squared error and the variance are the same thing. Again, when we think about the dartboard example, we showed that the accurate estimator is one that is precise and unbiased. So it makes sense. It's because here so we have negative expected value of theta tilde plus the expected value of theta tilde. So we're basically putting a zero term in. So for the unbiased estimator, again, the mean squared error and the variance are the same thing, which, going back to the dartboard example, makes sense given what we tried to describe about about the relationship between precision and accuracy. The ideal estimate is going to be the unbiased, or sorry, the ideal estimator will be one that is unbiased with the smallest possible variance. So if we have a collection of unbiased estimators for the same population quantity, we would want the one with the smallest possible variance. And we can find the variance of the quantity using the definition of the variance, which is given above. The idea of finding the minimum variance unbiased estimator, or rather the minimum variance unbiased estimator, is the most, or one of the most desirable estimators that we can find for a particular problem. So effectively, we are in search for the minimum variance unbiased estimator. And again, that's simply just an unbiased estimator with the smallest possible variance across a collection of all estimators. Okay, so let's just finish off by talking a little bit about what simple random sampling is. So at this point, we have talked about the idea of probability sampling in general. We have looked at some definitions of how we would collect an estimate from a probability sample, how we would determine if an estimator is unbiased across a small scale probability sampling scheme or probability sampling protocol. And now what we're going to do is start to look at techniques that are used in practice to find estimates from finite populations that are of a much larger size. So not three, or not a population of size 3 or a frame of size 3. Okay, so the first sampling protocol that we're going to talk about, which is probably the most popular sampling protocol, and the one that actually, as I've mentioned before, forms the basis for all of the different schemes that we're going to see in this class, is simple random sampling. Simple random sampling can occur, or there are two different types of simple random sampling. There is the version where we sample with replacement and the version where we sample without replacement. So we use the acronym SRSWR to mean sampling with replacement, which essentially means that if I have a sampling frame with, let's say 10 elements in it, Y1 through Y10, and let's say that I start to collect a sample of size 5, I pick out my first observation, which is Y2, for example. After I collect information from Y2, I place that unit back into the frame. So theoretically, a simple random sample with replacement could be composed of the same observation little n number of times. The simple random sample without replacement is a protocol where every single observation in the frame has the same probability of being selected, but you can only observe each element once. So the simple random sample without replacement would never have repetition of any element within the samples that it can produce. So it follows that an SRSWR is going to give you more samples than an SRS, period. All right. Okay, so the simple random sample without replacement selects n units from a frame such that each sample has the same probability of being selected. Okay, so this leads to n choose little n possible samples of the same size being possible. And it means that every single possible sample has the same probability of being selected, which is 1 over capital N choose little n. Okay. So on Monday, we will write down the inclusion probability for each of the different observations from an SRS. And then we will define the estimators for an SRS and give the properties of those estimators. So that is determine their variance and whether or not they are unbiased estimators. Okay, so we'll stop there. If anyone has any questions, as always, please let me know. If not, I will talk to you guys on Monday morning. So have a good weekend. And assignment 1 is due next Friday at the end of the day.